In this lesson, we're going to talk about exponential growth and decay models. So first here we just have the model equation that we use, and that would be a of t equals a sub naught times e raised to the kt. Your a sub naught would be the original amount, so that occurs when t equals 0. K is the constant growth, or k is a constant, and it's the growth or decay rate, and it cannot equal 0, and then t represents time. You will also see this law of uninhibited growth and decay uses this model function. It's the same thing, all right, but we're using n of t and n sub naught instead of a of t and a sub naught. But when k is greater than 0, we call that the law of uninhibited growth. And when k is less than 0, that would be decay. And there's some examples there for you. So let's dive into some examples here. A colony of bacteria that grows according to the law of uninhibited growth is modeled by the function. It's listed there for you, where n is measured in grams and t is measured in days. First, we're going to determine the initial amount of bacteria. Well, that occurs when t is 0, so we're going to find n of 0. So we're just plugging in 0. And that ends up just being whatever our n sub naught is, which is 100 grams. Next, what is the growth rate of the bacteria? The growth rate is the 0.045, which would be a 4.5% growth rate. And we know it's a growth because it is greater than 0. What is the population after 5 days? We're just going to find n of 5. So we're letting t equal 5 here. So 100 times e to the 0.045 times 5. You can plug that into your calculator. And we get about 125.2 grams. How long will it take for the population to reach 140 grams? So n of t is 140 equals 100 e to the 0.045 t. Well, the first step to solving that, we're going to divide both sides by 100. So we get 1.4 equals e to the 0.045 t. To solve this, we're going to take the natural log. So that would give us the natural log of 1.4 equals 0.045 t. And to solve for t, divide by 0.045. So t is the natural log of 1.4 divided by 0.045. So t is approximately 7.5, and we're talking about days here. And then what is the doubling time for the population? Okay, so our initial amount was 100, so the doubling amount would be 200. So we would do 200 equals 100 e to the 0.045 times t. You'll see here when we divide both sides by 100, we get 2 equals e to the 0.045 t. So when you're asked for the doubling time or tripling time, whatever it is, you could just set the left-hand side equal to 2, 3, however many times we are duplicating the population, because it ends up dividing out anyways. So let's see, t equals the natural log of 2 divided by 0.045. So t is about 15.4 days. All right. Next example here, a colony of bacteria increases according to the law of uninhibited growth. If n is the number of cells and t is the time in hours, express n as a function of t. Okay, well, we're following that law of uninhibited growth, so we would do n of t equals n sub naught times e raised to the kt. Part B, if the number of bacteria doubles in 3 hours, find the function that gives the number of cells in the culture. Alright, so we're doubling in 3 hours. So, like we just talked about, we can set the left-hand side is going to be 2. The right-hand side, I mean, we could assume we're starting with 1. We don't really know what we're starting with. We just know it's double the initial amount. So we're going to go 2 equals e raised to the k times 3, because we know it doubled after 3 hours. So if we solve that, we have the natural log of 2 equals 3 times k. So k equals the natural log of 2 divided by 3, which is approximately 0.23105. Okay, if you want to be as accurate as possible, you could leave k as the natural log of 2 over 3, or 1/3 natural log of 2. But if you round out to a decent amount of decimal places, it's going to stay pretty accurate here. So our function is n of t equals n sub naught, the initial amount, times e raised to the 0.23105 t. How long will it take for the size of the colony to triple? Well, we're going to have 3 equals e to the 0.23105 t, and we are solving for t here, so the natural log of 3 equals 0.23105 t, so t equals the natural log of 3 divided by our k, 0.23105. So t is approximately 4.75, and we're talking about hours here. And then part D, how long will it take for the population to double a second time? So really that's increasing by 4 times. You could plug in and do what we've been doing, but if it took 3 hours for it to double, it's going to double every 3 hours. So it's going to double a second time after 6 hours. Okay. Traces of burned wood along with ancient snow tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? Okay, so we need to use the fact that we know how long the half-life was. Alright, so 1/2 equals e raised to the k times 5,730 years. Taking the natural log of both sides, natural log of 1/2 equals 5730k. So k equals the natural log of 1/2 divided by 5,730. K is approximately negative 0.000120968. So our K is negative. We know that the amount of carbon-14 is decreasing because we're given the half-life. So we know a half of its life, how much is, how long it took for half of the life to be remaining. So we now know what K is, so our model is going to be A of T equals E. We don't really care what the initial amount was. Negative 0.000120968 T. So now we can use that. We're told that 1.67, they found 1.67% of the original amount, so then we want to know when was it cut down. So instead of its half-life, we know that 0.0167 of it is left, equals e to the negative kt. So if we're solving this, we got the natural log, 0.0167, negative 0.000120968t. Divide both sides by that k value. And you get t to about 33,830 years. So the tree was cut and burned about 33,830 years ago. Alright. Next, we have Newton's law of cooling. So we have our equation there, U of T equals capital T plus the quantity U sub naught minus capital T times e to the kt. U represents the temperature of a heated object at a given time. T would be that given time. Capital T is the constant temperature of the surrounding medium. U sub naught is the initial temperature of the heated object. And then K is a negative constant because it is cooling. So it's decreasing. So in our example here, an object heated to 100 degrees Celsius and is then allowed to cool in a room whose air temperature is 30 degrees Celsius. So we need to come up with our model here. So first thing we know is that capital T, the constant temperature of the surrounding medium, is 30 degrees Celsius. And the initial temperature of the object is 100 degrees Celsius. So if we plug that into our function, U of T equals 30 plus 100 minus 30 e to the kt. So U of T equals 30 plus 70 e to the kt. That's all we had from that first initial part. Well, now in part A, it says if the temperature of the object is 80 degrees Celsius after 5 minutes, when will its temperature be 50 degrees Celsius? So we need to use the fact that it's 80 degrees Celsius after 5 minutes in order to find our K. So find the value of K by saying 80 equals 30 plus 70 e to the K times 5. If we subtract 30 from both sides, we have 50 equals 70 e raised to the 5k. Divide both sides by 70 and we get 5/7 equals e to the 5k. The natural log of 5/7 equals 5k. So k equals the natural log of 5/7 all divided by 5, giving you a constant of negative 0.0673. So now our model is 30 plus 70 e raised to the negative 0.0673 t, and we can use that to find the temperature at different times or find the time it'd take to reach a certain temperature. So next here, when will its temperature be 50 degrees Celsius? we're going to take 50 and set it equal to our model there, 30 plus 70e to the negative 0.0673t. Subtract 30 from both sides. 20 equals 70e to the negative 0.0673t. Divide both sides by 70. We have 2/7 equals e to negative 0.0673t. So t is going to equal the natural log of 2/7 divided by negative 0.0673, which is about 18.6, and we're talking about minutes here. Part B, determine the elapsed time before the temperature of the object is 35 degrees Celsius. So we have 35 equals 30 plus 70e to the negative 0.0673t. Subtracting 30, we have 5 equals 70e to the negative 0.0673t. Divide both sides by 70, that ends up being 1/14. Equals e to the negative 0.0673t. So t is the natural log of 1/14 divided by negative 0.0673. So it will take approximately 39.2 minutes for the object to reach 35 degrees Celsius. Alright, and the last model we have here is a logistic model. P is representing the population, T is representing time. A, B, and C are constants that are greater than 0. And the model would be a growth if B is greater than 0, and a decay if B is less than 0. So in our example, fruit flies are placed in a half-pint milk bottle with a banana and yeast plants. Suppose that the fruit fly population after T days is given by that logistic model. State the carrying capacity and the growth rate. Alright, so from the original model, C represents the carrying capacity. So our carrying capacity is going to be 230 fruit flies. Our growth rate is the 0.37. Remember, if B was greater than 0, which it is, then it's a growth. So 0.37 would be 37%. And we are talking about per day here. Alright, the initial population is when T is 0. So P is 0. Plug in 0 for T. And you get that to be 4 fruit flies. So the initial amount that were put in that bottle was 4 fruit flies. What is the population after 5 days? We're finding P of 5. 230 divided by 1 plus 56.5 e to negative 0.37 times 5. You can plug that into your calculator, and you get about 23 fruit flies. Remember, when you're talking about population of something like an insect, animal, whatever, it's going to be a whole number, whereas the first one we did, we were talking about grams of something, so we could have a decimal for the population. So this ends up being about 23 fruit flies. And then part D, how long does it take for the population to reach 180? So we're going to take 180 and set it equal to our model. I'm going to multiply both sides by that denominator there, so I have 180 times all of that. divide both sides by 180, so we're left with that would be 23 over 18. Subtract 1 from both sides, and we have 56.5 e to the negative 0.37t equals, you could write it as a decimal if you want, but I got 5 over 18. Divide both sides by 56.5, we got e to the negative 0.37t equals, as a fraction, we would have 5 over 1017. So t is the natural log of 5 over 1117, all divided by negative 0.37. So t ends up being about 14.4, and that would be days.